I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth. No single space project in this period will be more impressive to mankind or more important for the long-range exploration of space. And none will be so difficult or expensive to accomplish.
It's one small step for man, one giant leap for mankind.
People often think that science took a back seat, and to some degree it had to the geopolitical aims. But still, it really got started very early. And indeed, for the last several missions, really beginning with Apollo 12, science became increasingly important to everybody within the organization. They realized that, yeah, we did what Kennedy asked us to do. We did the geopolitical thing, very, very important part of the Cold War psychology within the world's nations. But now let's get more out of it, and it really did take off, I think, from that point. That's the reason we had scientist astronauts, is because George Low and a few of the people around him were amenable to bringing that kind of expertise into the program. And when the National Academy made that recommendation to NASA that they select scientist astronauts, they had a friendly face and a friendly brain in George Low and Sam Phillips and others to do that. The main reason you want to send trained scientists or trained specialists into space to do whatever they are capable of doing as specialists is the same reason that you use test pilots early in a flight program, is that they have the kind of expertise necessary for that part of a program, and that was certainly appropriate for Apollo. But ultimately, we may have delayed a little bit too long in sending specialists to do the lunar science work, the field geology basically necessary to understand the moon. I think the main thing it has done is given us new insights, maybe not understanding, but insights into the early history of the Earth, the first billion years, because the moon has recorded what happened in the inner solar system during that period of time, and the Earth has destroyed it. It obviously happened on the Earth. The moon and the Earth have been co-orbiting for a long time, but right, almost certainly from almost the beginning of the solar system. So the moon is that kind of a record of history, particularly impact history. There's a basin on the moon that, again, hypothetically is about 3,200 kilometers in diameter, the Procolarum Basin. There is a well-recognized basin that's 2,500 kilometers in diameter called South Pole Lacan. And those kind of basins were forming in the first billion years here on Earth, as well as several hundred, probably more, several thousand basins that are at least 300 kilometers in diameter. That the Earth attracts far more of these asteroid impacts than the moon did. And that means that first billion years of time was very violent. Well, what else was happening? Complex organic molecules were getting organized at the same time and may even have become replicating during that period of time. Well, how did that happen? That's a question, not an answer. And we have to start thinking about that. Well, one of the possibilities is that in an aqueous environment, which the Earth is, when you create a lot of fine debris as a result of impacts, you're going to create a lot of clay. And clay, some forms of clay have very interesting properties in terms of organizing these organic molecules. They form a scaffolding, if you will, a substrate on which organic molecules can get organized and also start to pick up things like potassium, essential to life, and the like. And so it may well be that clay turns out, first of all, to be the dominant mineral species during this violent period, and two, it may be the basic catalyst that allowed life to begin here on Earth. And what do we see on Mars? Well, we see in the oldest rocks on Mars a significant amount of this right kind of clays. That's been detected by some of the orbiters that are now operating in the vicinity of Mars. The regolith, the debris layer covering the moon, which originates as a result of the superposition of various layers of ejecta, the maturation of each layer for a while, and then a new layer would come in. So it's a very complex stratigraphic or layered structure. And if that was happening, as we certainly thought it was, and know now that it did happen, then you're recording the history of the sun with each layer that time. If you can figure out a way to date those layers, then you start to understand how the sun has evolved over time. Well, I think we're finally getting to the point, particularly looking at the deep drill cores. The one that we took on Apollo 17 turns out to be the best. It's a complete core down to 3 meters depth. And if we start to look at those and the isotopic composition of various layers within that deep drill core, we're starting to see evidence, particularly in nitrogen ratios, that the sun is a primary reason for the maturity, the change in maturity of lunar soils, and that ratio, that nitrogen 15 ratio, nitrogen 15, nitrogen 14 ratio, is an indicator of how active the sun was at any given time. Well, it turns out in that deep drill core we have a layer that can be dated roughly to about 500 million years ago, because we have dated a crater that almost certainly created that layer within the regolith. And now it's a very loose date right now. It's 500 plus or minus 200 million years, and it's done by a process that Cahill calls topographic diffusion. He has developed a technique by which he can estimate the ages of craters by how much they've degraded over time. Okay. And with that 500 million year date in the core, we now have a chance to see whether or not we can date layers younger and older than that date by how much they have matured under the sun. Well, it also turns out that about 500 million years, there's very strong evidence in these nitrogen ratios that the sun changed its luminosity about 500 million years ago. And so that the soils that we see at the surface today are more mature than you would have expected had the sun not increased its luminosity. And that's pretty good data. That we know. Now the question is, what else was happening in the Earth-Moon system 500 million years ago, approximately? Well, we had the Cambrian explosion of life, both in quantity and diversity. That happened about 500 million years ago. We need more precise dating than we have right now for that hypothesis to be proven. But it still is a very interesting indication that Shoemaker was right. And the reason we started taking cores of the lunar regolith was because Shoemaker believed that we would get the history of the sun out of those cores. Now, it took us practically the whole Apollo program to figure out how to take cores. The reason being that the regolith itself is very hard to core. It's incompressible, and almost every technique we tried to use ran into problems. But by Apollo 17, we were able to get a 3-meter core and get a number of these drive tube cores, one of which is just now being opened by NASA, and a lot of us are looking forward to seeing if we're going to gain more information, not only about the avalanche where it was collected, but maybe more information about the history, the later history of the sun. Well, I've recommended, and still recommend, that NASA look very closely at the management environment that existed at the peak of Apollo, when we finally learned everything we needed to know in order to conduct a very complex, high-risk program of going to the moon and returning safely to Earth, John Kennedy's challenge to us. And we did that. And there were a number of ingredients in that environment that I think really need to be replicated to the degree possible. Number one, everybody was young. The average age of engineers, both in the private sector and in NASA, some 450,000 people, the average age was in the 20s. These were really young. The astronauts were among the older people, and the middle-level managers that were making everything happen were in their 30s. So that may be one of the, if not the most important ingredient, certainly one of them. The other is we had a management reserve that allowed us to stay on schedule, that avoided the political pitfalls of getting off schedule. That reserve was the baby, if you will, of Jim Webb, the Kennedy's administrator of NASA. He asked his engineers what they thought carrying out Kennedy's challenge of landing a man on the moon, returning him safely to Earth, would cost. And those year dollars, they came in plus or minus about $1 billion at about $8 billion. Well, when Jim Webb went to the OMB and went to Congress, he said 16. He doubled it. And so we were roughly dealing with 100% management reserve, and we used all of it. We really did. Because there's always unknown unknowns you come across in those kind of situations that have to be dealt with. And if you don't have the money to deal with them, you're going to slip schedule. There's just no other way to do it. And so that particular reserve was very important to Apollo. There were many others. Partly because everybody was young and the management had not gotten overly complex, a good idea could move very quickly to a decision. And sometimes overnight, these decisions were made. And that meant that the whole program was very efficient at dealing with test results that were adverse or with new ideas and things like that about how to accomplish the mission. And of course, extremely important was the ability to build a rocket with the capability of the Saturn V. That actually started in the Eisenhower administration. Ike, in January of 1960, over a year before Kennedy made his challenge to us, Ike ordered T. Keith Glennon, the then administrator of NASA, to begin the development of what was then called the super booster. That, there was another name, the C4, because it had 4 F1 engines in the first stage. That began the Saturn V well in advance of Kennedy's announcement. Had that not started under the Eisenhower administration, we probably couldn't have made the end of the decade schedule that Kennedy had asked us to. The role of a national space agency is geopolitical. The country has to take into account the activities of other nations, and in this case, particularly China. And so NASA is really a geopolitical entity. It was in Apollo, it has been since, and will be in the future. What is different now relative to Apollo is that there are commercial providers of launch services that did not exist at the time of Apollo. Those commercial providers, SpaceX, Blue Origin, and potentially others, can be a very important part of the future program, Artemis or whatever programs you have, and potentially can be much more efficient than a government agency in developing launch vehicles. The big challenge, though, for these commercial providers is to manage risks at a level that politically is viable. You're never going to eliminate the risks of going into space, and going into deep space enhances those risks significantly. That hasn't changed. The risks that Apollo had to manage in deep space are still there. That hasn't changed. The engineering capability to manage those risks has changed. We have a lot of new technologies we can use, but still the risks are still there. I'm not absolutely convinced yet that the private sector has come to grips with how to best manage the risks of launch, of operating in deep space, and so forth. And NASA has to be very careful as they integrate so-called commercial activities. They're not all commercial because there's a great deal of subsidy going on here, but nevertheless, integrating those kind of capabilities with their programs to make sure that the risks are still being managed appropriately. That is a political thing. One of the biggest risk is political risk, and you manage that by managing other risks. The most important sample was, with respect to resources on the moon, was collected by Neil Armstrong 50 years ago. This is the year of the 50th anniversary of Apollo 11. Neil and I worked together a great deal before and after his missions. And one time I asked him, why did he fill the rock box with dirt, with lunar dirt? And he said it looked empty at the time. He had put a really amazing collection of basalts and regolith breccias into that box, but it still, to him, looked empty. So he filled it with 10-0084. We like to talk in numbers in this sample world, but that 10-0084 really was the first major sample that showed us what kind of resources did exist in the lunar regolith. And that included all the resources that you need to operate in space. Hydrogen, water, because you can, if you heat the soil, which has oxygen in it, you will produce some of the hydrogen will come off as water. It has oxygen and nitrogen and carbon compounds. These are very important to the future of operating and living in space. And so that sample 50 years ago started to tell us that the moon could play, and almost certainly needs to play, a major role in human activity on into the future as it encompasses this so-called new ocean of space. In addition, that sample showed that there was helium in the soil, and a significant amount of a light isotope of helium called helium-3. Helium-3 is an ideal fuel for fusion power once the technologies are developed in order to use it. Fused with itself, it produces no radioactivity. Fused with deuterium, it produces a very small amount of residual radioactivity in the reactor itself. And the radioactivity comes from having neutrons. And when you don't have neutrons, or what they call aneutronic fusion, then you don't produce any radioactive waste that you have to deal with. It also can be much more efficient because you can convert the fusion products directly to electricity. You don't have to go through a heat cycle in order to produce power. So if you had it here on Earth, we'd be using it today, I'm convinced. But you don't have it here. It's just not available. The atmosphere and the magnetosphere of the Earth keep helium-3 ions from being available. The moon does collect these helium-3 ions, and there is enough to potentially be commercially viable. The private sector investors might well, at some point in the future, see that there was a value to harvesting helium-3 from the moon and using it in fusion reactors here on Earth. Helium-3 has another interesting application, side benefit. If you have it coming back to Earth, it can be used for lung diagnostics. It is an ideal way to get very high-resolution images of the human lung because it can be polarized. And as a result, you can start to deal with this extraordinary threat human beings have of lung cancer. If you can diagnose lung cancer early through helium-3 diagnostics, then you have an opportunity to cure. Right now, only 19% of people who develop lung cancer survive. That's the worst record of any cancer that we have, practically any cancer, with maybe the exception of pancreatic cancer. And so the advantage of having helium-3 back here on Earth are really immense. Now, can you do it in a cost-effective way? And that's the question. But once you are established producing resources on the moon, then a lot of things start to become possible, including Mars exploration. People who think you're going to go directly to Mars, I think, are whistling Dixie, pardon the expression. It's going to be very, very tough. Mars is a long way away. One way of shortening the transit time is helium-3 fusion rockets. And to shorten that so your exposure to space radiation is less. And the adverse effects of microgravity or zero gravity. Mars also has only enough atmosphere to cause problems and not enough to help you dissipate energy as you enter it, like the Earth does. And so we need to deal with all of those new engineering challenges, operationally as well as from the physiologically. And I think we will. I think we'll figure all that out. But the moon is in the critical path to figuring those kind of things out. It's very important to recognize that one of the successful ingredients of Apollo was the response of young people to Sputnik 1. The launch of Sputnik 1 created what has correctly been called the Sputnik generation. Many, many young men and some young women became extremely interested in space. The October Skies movie is an excellent example of that kind of interest, but it was throughout the country. And those young men mostly came into Apollo as the engineers and to some degree the scientists of Apollo. They joined with a generation that was coming out of World War II with significant management experience, joined with another generation that had populated the National Advisory Committee on Aeronautics, which provided the core management capability, really coming out of the management that the Space Task Group had exerted on the X-15 program. That's where a lot was learned, but you really had this core foundation of young people who were interested in engineering, who had the mathematical tools in order to participate in engineering and to participate in Apollo. That base, I think, is still there. It just has to be mobilized. The key element, though, in any education program, we talk about STEM, but it's the M that is key. If you do not have, as an individual or as a country, a strong base in mathematical fluency, then all sorts of things become impossible. As an individual, there are whole careers that you can't even entertain entering if you don't have a mathematical background, a strong mathematical background. Now, the other things, the science technology side of things, it's wonderful to have. It shows you how to apply mathematical tools. Most of that you gain, though, once you go out and really start working in engineering. It's like people try to teach systems engineering. You can't teach systems engineering, in my opinion. You got to learn systems engineering in the real world. And I think Apollo showed that in spades. We created systems engineers that had never even knew what that phrase meant, out of the strong base of education that came out of World War II, the Cold War, and also the launch of Sputnik 1.